In this reference guide, we'll be looking at multiple right triangles that exist within the same problem. So in these questions, we won't just be solving a single right triangle as we've been doing so far. We'll be seeing what happens when two or more triangles are kind of stacked on top of each other or are kind of found within one another. So we'll be looking at how to solve problems that involve more than one right angle triangle. And the good news about this is we'll still be using sine, cosine, and tangent. That won't have changed, but we'll just maybe sometimes have to use them 2 or even 3 times within the same problem. So let's take a look at what this will look like. At the top of the reference guide, you'll see a new term. That term is angle of depression. The angle of depression is the angle below the horizontal that an observer must look in order to see an object that is lower than the observer. Now, you can see in this diagram where the angle of depression is. It's found between the horizontal line and the diagonal line. What's important to note is that the angle of depression is not found at the top of a right triangle. So this angle here is not the angle of depression. The angle of depression exists between an imaginary horizontal and the hypotenuse of this triangle. So this is where we would find the angle of depression. And it's a common mistake that students make. They misidentify the angle of depression as the top angle in a triangle. But it's not. It's not that original angle. It's not this one right here. It's just outside the diagonal line and between the imaginary horizontal. And it's important to remember that. Because we don't want to put our angle of depression in the wrong place, because those two angles obviously will not be the same unless they both happen to be 45 degrees, which they wouldn't be. So as I mentioned before, the nice thing about this is there's no new skills that you need to learn within this reference guide. We're still going to be using sine, cosine, and tangent, so we're still going to be dividing opposite and hypotenuse if we're talking about the sine ratio, adjacent and hypotenuse if we're talking about the cosine ratio, and opposite and adjacent if we're talking about the tangent ratio. So nothing has changed there. It's important to remember something that was noted in an earlier reference guide. If you do like these magic triangles, as they're called, then that's fine, but you will not be given them in your formula booklet. So if you do like the magic triangles as a means for manipulating equations, then that's okay. However, they're up to you to remember, as they won't be given to you on any assessments or in your formula booklet. Okay? So when we solve these problems, we're even going to use a similar series of steps as we used previously. However, this will obviously be more involved because now we have more than one right triangle involved in the problem. So our first step, as it always was and always will continue to be when solving trig problems or just math problems in general, is if you can draw a diagram, draw a diagram. So if I've given you a diagram, then obviously you wouldn't have to do step number 1, but if you're given a problem and no diagram is provided, your first job is to draw one. Step 2, properly label your diagram, ensuring that you've identified all angles and sides and identified the right angle as well. You want everything in the right place, and that makes sense because if you're labeling things incorrectly, no matter how nice your triangles were, then all the math you do afterwards won't apply if everything is improperly labeled. Step 3 is going to carefully reanalyze the question once you've built your diagrams and figure out exactly what side or what angle on the diagram you're looking for. And it may be multiple sides or multiple angles even, depending on the question. And this note right here is really important, and we'll see this come into play a little bit later. If you have two triangles that are stacked on top of each other, sides that are shared between the two triangles are often really important. Oftentimes, one of your first steps, if not your first step once your diagram is drawn, is going to be to solve for a side that's shared between triangles. Step 4 is where you do your math. Using the information that's given in conjunction with your ratios, you're going to solve all necessary sides or angles. And as I said before, this won't be just a single mathematical operation this time. It's not just going to be sine once or cosine once or tangent once. You may have to use one multiple times, or you may have to even use multiple trig ratios. So you may use like cosine and tangent in the same problem. It will depend on the question. It will depend on the triangles you've drawn. Step number 5 is something that's applied since day 1. If you're solving a word problem, you end with a concluding sentence. And hopefully you remember that, and you're doing that just naturally at this point. So now let's look at a problem. So we have solved single right triangle problems already. We've done a whole bunch of them in the first couple of reference guides and the work that came with those. So we should be good at solving single right triangle problems, and that's all this is, except you're going to have to do it maybe twice, maybe 3 times within the same problem. But what you want to do is break these questions down and find the individual triangles that exist, and then solve them accordingly. So this question reads, a student wanted to know the distance between 2 particular carvings on a spirit pole. She measured the angle of elevation of each carving 15 meters from the base of the pole. And she drew the sketch below. What is the distance between the carvings to the nearest tenth of a meter? So we are looking for this distance right here. That's what we want. Well, that distance does make a triangle with the starting point where the wires are anchored to the ground. But we don't have a right triangle there, so it's not something we're going to be able to solve. However, if we look, we can see that we actually have a big right triangle here, and we have a smaller right triangle here. And so you can see now that you have multiple right triangles existing within the same question. The base of both of those triangles is 15 meters. That's nice. That's a shared side between the blue and the red triangles. The only thing that's different is that angle at the bottom, that angle of inclination, which is 35 degrees in the blue triangle and 45 degrees in the red triangle. So what we need to do is we need to know how tall the vertical leg of each triangle is. If we know how tall the blue triangle is, and we know the height of the red triangle, the difference between those heights will give us the value that we've labeled as x. So as I said, we're going to solve this problem twice. So let's start. We'll just make a little legend. And let's start with the red triangle. The red triangle has an angle of elevation of 45 degrees, and it has a base of 15 degrees. Well, this base is adjacent to the angle, and we want to know its height, which is opposite. It's opposite to the angle. It's clear across the triangle. So we're going to use the tangent ratio, where we're solving for opposite. And if we look up at our magic triangles, or we know how to manipulate the equation, and we've done this enough that we should be fine with either of those means of getting to the formula, we know that opposite is equal to tan theta multiplied by adjacent. And remember, before you solve any problem, whether it be in Math 10 or any course, if you're using a formula, the first thing you do is you list the formula. So tan of 45 degrees, which we've talked about, it's came up a couple times already. We know that's equal to 1 multiplied by 15 meters. So we're going to have 1 multiplied by 15, and we know then that the vertical leg of our red triangle is equal to 15 meters. So that's good. Now let's take a look at the blue triangle. Well, the blue triangle is still has an adjacent base, so the 15 meters is adjacent, and we still want the opposite. We're doing the same thing. The only thing that's going to change is our value of theta in this question. So opposite is equal to tan of theta multiplied by adjacent, where theta is now 35 degrees. Our adjacent is still 15 meters. And we're going to just need to take a second and put this in the calculator. So tan of 35 multiplied by 15 is going to be 10.50 meters. And now we need to just figure out the distance. And maybe you can do that in your head, but if not, we can just do a little side calculation here on the side, and it works out to be 4.5 meters. So we need to bear in mind that this is a word problem, and as such it requires a concluding sentence. So we would say, therefore, the marks are 4.5 meters apart. Okay, and what I want you to notice about this question is even though the diagram is more complicated than just seeing a single right triangle, and the word problem does seem a little bit more confusing than maybe did some of the previous problems we did on, say, reference guides 1 and 2, all you're basically doing is looking at two individual right triangles. And you can see those by the different colors I used. One is red, one is blue. And then you're just solving right triangles using the tangent ratio, which is what we spent all of reference guide 1 doing. So really, it's not too bad. It ends up being a decent question, just a little bit more work than maybe we had done before. Okay? So that's our first question. Now if you flip the reference guide over or turn to the next page, you'll see another question that involves multiple right triangles. So let's take a look here. A falcon is sitting in a tree 11.4 meters above the ground. There is a squirrel and a chipmunk below. From the falcon, the angles of depression to the animals are 36 degrees and 47 degrees respectively. How far apart are the squirrel and the chipmunk to the nearest tenth of a meter? So if we're drawing our diagram, we have a falcon that's sitting in a tree, and we know that the squirrel and the chipmunk are below. We know that the angle of depression to the squirrel is 36 degrees. We know that the angle of depression to the chipmunk is 47 degrees. So the chipmunk in our diagram is going to come first. The squirrel is going to be over there. And one way we would know that we didn't really discuss earlier, is your angle of depression and your angle of elevation are always equal to one another. So we know that since the chipmunk has a 47 degree angle of depression, it also has a 47 degree angle of elevation up to where the falcon is sitting. So we know that it will have a more severe angle, so it would be listed first. So when we draw our diagrams, we're going to have, we'll use red to the chipmunk, and we'll use blue again, that was fine last time, to the squirrel. And these two triangles are both right angles, or both contain right angles. So our diagram looks something like this. Well, we know that the chipmunk has a 47 degree angle of depression, which is up here, but it's also down there. Angle of depression and angle of elevation are the same. So that means that if that's 47 degrees, then this one must be 36 degrees. We also know that the tree is 11.4 meters tall. So I'll do that in blue just so we can see it fine. And there we go. So our first step to this problem was drawing a diagram, and there's our diagram. And the bases of the triangles would be lying on top of one another. I just drew them a little bit separate so we could easily distinguish the two colors. So, much like we did last time, we have two triangles that we need to solve. One of them is red, one of them is blue. And the only thing that's different, just as it was last time, is our angle of elevation is different. So in the red triangle, it's 47 degrees. In the blue triangle, it's 36 degrees. So we're going to need to solve it. And now when we label our sides for our red triangle, the 11.4 meters is opposite to our angle. It's on the other side of the triangle. And we're solving for the base. We want to know how far apart the squirrel and the chipmunk are. So in this case, it's going to be tan again because it's opposite and adjacent. Except this time, we're solving for adjacent. And adjacent is equal to opposite divided by tan theta. So adjacent, therefore, is equal to 11.4 meters divided by the tan of 47 degrees. We know tan of 47 from previous discussions is just a little bit more than 1. So we know our answer is going to be just a little bit less than 11.4. And when we put it in the calculator, it's 10.63. So that's how far the chipmunk is sitting from the tree. Well, now we need to find how far the squirrel is sitting from the tree. And we'll be able to check and make sure our diagram is correct here, because the squirrel should be further away from the chipmunk. If he's not, we've done something wrong with our diagram that we would have to revisit. But everything should work out fine. So adjacent equals opposite over tan theta, just like it did last time. The opposite's still 11.4. Because the height of the tree is clear across the triangle from our 36 degrees. Our theta now has changed. It's changed to 36 degrees. So we're going to divide this out. And we know that tan of 36 is going to be less than 1, which means that number should get bigger, and it does. It becomes 15.69 meters. Now, at the end of this, we're being asked to round to the nearest tenth of a meter. I've left everything to the nearest hundredth just for precision, and we'll do that rounding to the nearest tenth at the end. It might not make a difference, but sometimes it does. So 15.69 subtract 10.63 gives us 5.06 meters, which, when we round to the nearest tenth of a unit, is equal to 5.1 meters. And now it was a word problem, so we treat it as such by writing a concluding sentence. So we would say, therefore, the animals are 5.1 meters apart. Okay, and those are just a couple examples of multiple right triangle problems. But what's important to note about these problems is you're not really doing too much different than what we had been doing in previous reference guides. Instead of solving for 1 triangle per question, now you may have to solve for 2 or sometimes even 3. Otherwise, you're still using sine, cosine, or tangent. You're still drawing diagrams. Nothing has changed too much from what we looked at in previous reference guides.